Okay, next we have another quantity which are very essential in the rectification of in the rectifier, which is ripple factor. Actually, the current obtained at the output of full wave rectifier is not purely DC. Like if we have this is the input signal. Here we have the input voltage. This is the Vm, and this is omega t. Then the output voltage V naught just look like this. It contains both AC and DC component. So DC component is because it's a unidirectional, all are positive, and AC component is like it's going from started from 0, reaches to a maximum value, and then again goes to 0, and then again it's increased to maximum value, and then again goes to 0. So this behavior is behavior of alternating current, while this unidirectional current, like the output voltage is always positive. It's the characteristic of DC voltage. So the output is a combination of both AC and DC component, which we call ripple or pulsating current. This is called pulsating current. It contain both AC and DC component. Now ripple factor, it's tell us about the degree of pulsation, or the degree of pulsation, is named as ripple factor. Now it is basically a measure of purity of DC output of a rectifier. We can also say that this ripple factor measure the percentage of AC component in the rectifier output. Tell us how many percent of the AC component exist in the output of a rectifier. It is denoted by the symbol gamma. This is the ripple factor, which is equal to, by definition, we can define it as root mean square value of AC component of output current or voltage divided by DC value of the output current or voltage. I'm not going into the detail of this one because we already did it in the case of half wave rectifier. We have a very long proof. Just go and repeat your previous video, but I will write a direct equation. After doing a lot of calculation, we reach to this equation, and the equation is this ripple factor is equal to IRMS square over IDC square minus 1 square root. This is not a direct equation because there are many steps which I'm missing here, because I already We already did it in the case of half wave rectifier, like by calculating the ripple factor for the half wave rectifier. We did this one, we reached to this point. This is one of the equation. Now in case of full wave rectifier, IRMS, like the root mean square value of the current is Im over square root 2. And similarly, the average value of the current or DC output current is also given by 2 Im, where Im is the maximum current or the peak value of the current, divided by pi. If I put these two values, this value and this value here, then the ripple factor will be equal to Im over square root 2 square. This is RMS value of the current, which is given here, divided by the average value of the output current or the DC current is 2 Im over pi square minus 1, and we have this square root. So if we solve it, we finally get, because this Im cancel with this Im, and we have this pi square in the denominator here, so it goes to the numerator above, which is pi square divided by, we have 8 here, square root minus 1. If we solve it, we get the value of ripple factor, which is 0.48. I am not sure how much is the ripple factor for the DC current. For that, for this is for the full wave rectifier, while for the half wave rectifier, the ripple factor is 1.21, which is much bigger than this one. So it means that in half wave rectifier, the AC components are dominating the DC component, while in full wave rectifier, the DC component is dominating the AC component of the output voltage, output current. So this is the ripple factor. Now we have the final or last subtopic of this full wave rectifier, which is peak inverse voltage. Peak inverse voltage. What is we can represent it by PIV, peak inverse voltage. The maximum voltage that a diode can withstand in reverse biased is called peak inverse voltage. Now I will draw the full wave rectifier diagram again. Here this is the primary coil of the transformer, and we have one diode, and here we have the second diode, and these two diodes are connected, and this is the central tap. So we have a third terminal which is connected to the load resistance RL. So here we have the V0, which can be measured here by using a voltmeter. Now if positive half cycle of the output signal reach to this central tap transformer or the primary coil of this transformer, then this will become positive, which we already discussed, and this one become negative. So here we have negative and here we have positive. Now in this case, D1 is forward bias, I it's a closed circuit, I it's on, and D2 which is reverse bias, because P side of D2 is connected to the negative terminal and inside to the positive. So this is a reverse bias case. While P side of P region of this D1 diode D1 is connected to positive terminal and N to the negative terminal. So this is forward bias. So in this case the current is flowing from positive to negative. So the direction of current is this one. So here we have maximum voltage and here we have maximum voltage in these 2 points. Now D1, this is on, so it's on, or it's a closed circuit, or we have a short circuit here. So this I can represent this by this vector. This is open, so there is no connection between these 2 points. So we have this, the final diagram of this circuit is this one. So here we have the central tape. Here we have the V0. Current is flowing through this one. Now here we have this A, here we have B, this is C, this is D, this is E, and this is F. So this is closed circuit, so there is no potential difference here, so I connected directly here. Now this is a closed open circuit because this is forward bias, so current is not flowing. So it's an open circuit because there is no connection, so current cannot flow in this way or in this way. So the current is flowing only in this way. Now applying this is positive, this is negative. So this is negative, this is positive. So if this is negative, then this will be positive and this will be negative because current is flowing from positive to negative. So current is flowing in this way. Now applying Kirchhoff law, to the loop. And the loop is AB, DF, CA. Not AB, AD, FCA to this loop. So I'm going in this way. So from negative to positive, we go from negative to positive, and the value will be positive. If we go from positive to negative, then the value is, we will take the value as to be negative. So here look at this. I started from point A, there is no drop of voltage or anything else. So here if I reach to this point, this is positive and I am going to the negative side. So there is voltage V0, which I will take to be negative, minus V0. And then I reach to this point here, this is negative, this is positive, and in between we have Vm. So the Vm should be positive, which is equal to 0. Vm is equal to V0. Now here we have the peak inverse voltage, PIV, in this point, because this is the reverse bias, this diode is in reverse bias. So the maximum voltage that this reverse bias diode withstand is called peak inverse voltage. Now to calculate the peak inverse voltage, we apply Kirchhoff law to the loop, which is B E F C B. B E F C B. Now we have, this is negative, so this should be positive, this is negative. So I'm starting from here, so here I am going from negative to positive, and here we have PIV, which is positive there. Then I will move to E, there is no voltage drop or anything else, then F, and from F I am going towards C. So here I am going from positive to negative, so this V0 should be negative, which is equal to 0. and then yes, not this is V naught, and then again I am reaching to this end, and from here I am going from positive to negative, but here inside in between this we have the maximum voltage Vm. So we have this Vm, which is again also be negative, which is equal to 0. Now P IV minus V naught value is equal to Vm, and minus Vm again is equal to 0. PIV minus 2Vm is equal to 0. PIV, the peak inverse voltage, is equal to 2V. While in the case of half wave rectifier, this is for the full wave rectifier. While for the case of half wave rectifier, the peak inverse voltage was just Vm. So it means that in case of full wave rectifier, we need a maximum voltage. This diode can withstand with a maximum voltage like 2 times Vm. Sorry, this is PIV. I think I have to repeat this part again. We will apply the Kirchhoff law to the loop BEFCB. BEFCB. So I am starting from B. So I am going from negative to positive. So the PIV value should be positive. If we go from negative to positive, then we take it to be positive. And then again from E to F, there is nothing else. And then if I am going from F to C, then here I'm going from positive to negative. So this V naught value should be negative. And from this C, if I'm going towards B, then again I am going from positive to negative. So here we have Vm. This Vm is negative because we are going from positive to negative, which is equal to 0. But V naught value is Vm. So here I put the V naught value here, which is Vm, and Vm itself. So PIV is equal to Vm minus Vm, which is minus 2Vm is equal to 0. PIV is equal to 2Vm. This is for the full wave rectifier. While for the half wave rectifier, we have the PI value, which is Vm. So it means that in half wave rectifier, we need a minimum voltage, a lower voltage to operate the circuit. While in the full wave rectifier, we need a maximum value. Its value is 2Vm to operate this circuit. So this is all about peak inverse voltage. Thank you. This is the end of our full wave rectifier. Next we will discuss the bridge. We will discuss about, in the next video we will move towards what we call it full wave bridge rectifier. Thank you.